you, Chair, and hi everyone. Welcome to my presentation. So today my presentation will be a short and pretty straightforward one because my concept is pretty simple and not complicated. So basically, what I'm going to present is I'm going to take advantages of the free ammonia concentration in hydrolyzed urine, especially the concentrated ones, to mitigate, or not mitigate, to reduce the biofouling in reverse osmosis. So we all know that in fresh urine, they contain a lot of urea, especially 20-something grams per liters of urea. But hydrolysis of urine takes place very quickly. So all of this urea will convert to hydrolyzed to ammonia, ammoniacal nitrogens, and basically the concentration of ammoniacal nitrogen in hydrolyzed urine is around 3 to 6, can be even higher. And because of the hydrolysis process, most of the the urine will become high pH, and at this pH, around half of the ammoniacal nitrogen will become in the form of free ammonia. And the interesting part comes in, and we all know that free ammonia will be biocided and will inhibit the growth of the bacteria. So from this one, we try to take advantages of the characteristics of free ammonia to reduce the biofouling while we concentrate the urine. Okay, but first, why we are going to concentrate the urine is because urine is 97% of water, and if we transport the hydrolyzed urine directly for fertilizer usage, it will be very high in the transportation cost, and especially if there is a transportation between cities to the farmer area, then the cost will be very high and not economical feasible. So that's why we need technology to concentrate the urines. So why we choose reverse osmosis as our technology is because when we look, is because of three aspects. First is because the nutrient recovery, which is the most important one. If we lose a lot of nutrients during the concentration process, there is no point doing that. So when we look at the reverse osmosis, it shows that although there is some loss in the nitrogen, but the potassium and the phosphorus recovery is pretty high, so 95% above. And then when we look at the water recovery, means that the higher water recovery means if we have higher water recovery, means that we can concentrate the urine more. So by using the reverse osmosis technology, we can get like 75% of water recovery. That means we can reduce the volume of the urine by a factor of 4. Then most importantly, when we look at the energy consumption, the kilowatt per hour of meter cube of urine is around, of reverse osmosis is around 5, which is significantly lower compared to other technologies. So because of the advantages that are offered by the reverse osmosis, so this is the reason why we chose this technology. However, one of the obvious drawback of reverse osmosis is that the fouling. So everyone knows that if you concentrate or you process some solution that contain high concentration of nutrient, biofouling is a problem that we can't avoid. However, there is some previous report that try to concentrate urine using reverse osmosis, and they found that the fouling can appear as soon as 24 hours. So this means that if we can't solve this problem, we cannot use this technology to concentrate urines. So, but from the other side of the story, if we concentrate urine, that means the free ammonia in the urine will increase automatically because we remove water. So from this point, we think that maybe we can operate a reverse osmosis in a very highly concentrated mood, so that the biofouling of the reverse osmosis can be reduced all the way, or at least we can delay the biofouling from appearing. So from this one, we design experiment. So this experiment is very simple. First, we collect some real urine, then we let it hydrolyze, then we concentrate the urine to the 3 types of volume reduction factor, which is 1.5, 2.5, and 4. So all these represent a different degree of water removal. So of course the 4 times water reduction is the most concentrated one. And then we introduce also we get some unconcentrated urine as a control. Then we run all this urine for 7 days of operation to expose the urine to reverse osmosis to see how the fouling will appear. Then in this experiment, we will recirculate the urine for 7 days, non-stop, 24 hours. Then after 7 days, we will quantify the fouling. So first, before I run into the result, I want to show that if after concentration, after the concentration of urine by reverse osmosis, there is certain degree of loss in the nitrogen that I mentioned just now. So as you can see that from the unconcentrated one to the 4 times concentrated, the urine should be 4 times more between 1 and 4, but it's not obviously a linear relationship. So there's a degree of loss, but this is normal. Then by this one, after 7 days of operations, we found that the flux decline in the most concentrated urine is significantly lower compared to the unconcentrated one. So the black dot means that we run the reverse osmosis membrane with the unconcentrated urine. So you can see the flux decline is very rapidly. At day 7, the flux is declined for about 35%. And then, but if we use the most concentrated one, the flux decline is pretty slow. And then the graph at the left-hand side, it shows that the absolute flux, which is the starting flux of the permit, is very low for the most concentrated one compared to the unconcentrated one because of the osmotic pressure in the concentrated urine. So this is the figure of the membrane after 7 days of operation. So we can see that in the unconcentrated one is the full of the fouling. At this point, I can't say that it's bacterial because I haven't done any analysis, but at least you can see that from the appearance of the membrane, it's become more and more clearer. So with using the 4.4 gram per liter of MH3, the membrane become really clean. But I cannot say it's absolutely clean because we still can see a black dot over there. This cannot observe with camera. Then after that, we send our membrane for microscopic analysis and stand with the live dead bacterial pits, and we show that with the unconcentrated one, the foulants on the membrane, which is the brown color thing, are full of bacteria. We process the owl using the unconcentrated urine, but then the form and the abundance of the bacteria reduced with the concentrate of urine. So you can see with the unconcentrated one, the bacteria is in the colonized form, and there is a lot of bacteria. Then starting increasing the free ammonia, the bacteria become more and more scattered. At the end of the day, it's just a little of bacteria over with the most concentrated urine. So of course, we have to get some quantitative result. We can't only judge the research based on the qualitative result. So then we send the samples for flow cytometry analysis, and it showed that in the unconcentrated urines, the bacterial number on the owl membrane is significantly higher, 4 magnitude higher compared to the most concentrated one. And what significant is, with using the most concentrated urines, that bacterial increased significantly from 1% to 68%. So it also shows that the free ammonia have the ability to inhibit, at least to kill the bacterial, so that the bacterial cannot reproduce. Therefore, we can reduce the biofouling. So yeah, I think that's all from me.
Thank you, Chen. That's an excellent final talk of our session. Our session starts with free ammonia application by Professor Xiang, and the final presentation by you extending its application to biofouling. So do you have any questions from the audience for Chen? Maybe I start with one. So did you look at the mechanism of these three FA biocycle effects? Is it killing bacteria, or is it degrading the EPS or these?
Okay, so basically from the theoretical part, we know that the free ammonia can inhibit the growth of bacteria through the proton imbalancing mechanism. So bacteria, if this one takes place, bacteria need more energy to pump out the potassium in order to maintain the pH balance in cell and outside of the cell. So this one will consume, it will require you increase the energy consumption of bacteria. So we guess from this point, the reproduction of the bacteria slow down because the energy was used to pump out the proton instead of used for reproduction. This is proven. And then another thing is, we all know that in high free ammonia concentration, it can lysis of EPS. So I mean, this is also, I guess, we guess, because we have no evidence, we guess that's also one of the mechanisms that why the membrane on the with the more concentrated urine is so clean, because literally no EPS on that. Yeah. So one of the evidence that I want to want to show is that we also did some FTIR analysis to prove whether there are any EPS on the membrane. So we show that even though the result is not in the slide, but I want to share it verbally. It showed that with the most concentrated urine, the composition of this membrane is almost identical to the clean membrane, virgin membrane. There's not used one. So it means that the EPS on this membrane is almost absent. Yeah.
Thank you. Yeah, I think probably it's more on EPS, like because your 1.9 gram per liter of free ammonia is already way higher than what's being reported in the previous study. So
true.
You know,
normally in the anaerobic digester, 1.1 gram per liter of ammonia can already inhibit the growth, but obviously in the research it needs higher. Yeah.
That's very interesting.
Yeah.
Thank you for your presentation. I have a simple question. In case of for the solution, I think the flux was very low compared to one volume reduction fold. Why could you reduce the pressure to decrease the flux, and then the total water pass through the membrane will be reduced? Then you may impact on the membrane volume.
That is a good question. Okay. So from this graph, we can see that if we use a more concentrated urine, the flux is very low. So I think there's some membrane expert here. They show that if we running the membrane if under the critical flux, of course it can reduce the biofouling. But we also did another side experiment with running the 4.4 gram per liter of nitrogen free ammonia with the flux similar to this one, and we show that the flux decline is very slow. And then one of the most important thing is the evidence from the flow cytometry. If free ammonia cannot prevent the biofouling, and the biofouling reduction is purely due to the reduced flux, then that bacteria will not increase, it will remain. Because from the literature, reduced flux indeed can reduce biofouling, but it cannot kill bacteria, or at least the fraction of that bacteria will not have this significant difference. So from all this evidence, we can conclude that yes, reduced flux can reduce have some effective in reduce biofouling, but the main contributor is free ammonia.
Yes, thank you, Honest. Have you tried to watch the membrane surface with the flux recovered or not?
Sorry, can you?
Have you tried to wash the membrane surface?
Wash the membrane. No, we didn't wash the membrane. So every time we run the experiment, we run it 7 days continuously, and then we stop the experiment. Yeah.
Thank you. That's very promising.
Yeah.
Please join me to thank Chen for this. That will conclude today's this session, and I think our lunch is away. Thanks everybody for coming.